everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to understand reasons for the trends in thermal stability of the nitrates and the carbonates of the elements in groups 1 and 2 in terms of the size and charge of the cations involved. And then we're going to understand the formation of characteristic flame colours by group 1 and 2 compounds in terms of electron transitions. And then we're going to understand experimental procedures to show patterns in thermal decomposition of group 1 and 2 nitrates and carbonates, and also flame colours in compounds of group 1 and 2 elements. Now we're going to talk about the thermal decomposition of group 1 and 2 carbonates. So the definition of thermal decomposition is the use of heat to break down a reactant into more than one product. And so for the thermal decomposition of group 1 and 2 carbonates, this is what we have. So the ease of thermal decomposition decreases down the group. And group 2 carbonates decompose on heating to produce group 2 oxides and carbon dioxide gas. They become more thermally stable going down the group, and this is because as the cations, so the positive ions, get bigger, they have less of a polarizing effect on the negative carbonate ion, and so it doesn't distort it as much, and so there's less covalent character. This means that the CO bond is not weakened as much, and so it does not break down as easily. For group 1 carbonates, they don't decompose with the exception of lithium. They only have 1+ charges, so they don't have a big enough charge density to actually polarize the carbonate ion. And so lithium is the exception because its ion is small enough to have a polarizing effect on the negative carbonate ion. So there are a number of experiments that can be done to investigate the ease of decomposition. And one is to heat a known mass of carbonate in a sidearm boiling tube like the one in the diagram and pass the gas produced through lime water. And then you time for the first permanent cloudiness to appear in the lime water and repeat for different carbonates using the same moles of carbonate and the same volume of lime water. And the reason why the lime water goes cloudy is because of the carbon dioxide which has been produced. And now we're going to talk about the thermal decomposition of group 1 and 2 nitrates. So group 2 nitrates decompose on heating to produce group 2 oxides, oxygen and nitrogen dioxide gas. And so you'd observe a brown gas which evolves, and this is the nitrogen dioxide, and the white nitrate solid is seen to melt to a colourless solution and then re-solidify. So for example here we have magnesium nitrate and it forms the magnesium oxide, nitrogen dioxide and oxygen. Now group 1 nitrates don't decompose in the same way as group 2 nitrates. They decompose to give a nitrate 3 salt and oxygen. So for example, we have a nitrate 5, we have a sodium nitrate 5 going to decompose into a sodium nitrate 3 and oxygen. However, lithium nitrate decomposes in the same way as all the group 2 nitrates do. So it forms the oxide, so lithium oxide, and nitrogen dioxide and oxygen. Now, the trend is that the ease of thermal decomposition decreases down the group. And the explanation for this is exactly the same as it was for the carbonates. The magnesium nitrate decomposes the easiest because the Mg2+ ion is the smallest, and so it has the greatest charge density. And this means that it causes more polarization of the nitrate anion, so the negative nitrate ion, and it weakens this NO bond. And so less energy is needed to overcome the bond. And so thermal decomposition is easier. Group 1 and group 2 compounds actually give off different flame colours when we perform flame tests on them. So the method we would do this would be firstly to use nichrome wire because it's an unreactive metal, so it won't give out any flame colour, so it won't interfere with our test. And then we clean the wire by dipping in concentrated hydrochloric acid and then heating in a Bunsen flame. And if the sample of compound is not powdered, then we grind it up. And the last step is to dip the wire into the solid and put it into the Bunsen flame and observe the flame. Now the colours we should get, you need to remember. So lithium has a scarlet red colour, sodium is yellow, potassium is lilac, rubidium is red, cesium is blue, magnesium has no flame colour, calcium is brick red, strontium is red, and barium is apple green. And you really need to make sure that you know all of these off by heart. So why do we have different flame colours? Well, in a flame test, the heat causes an electron to move to a higher energy level, and that's because we're providing it energy. And this electron is unstable at this higher energy level, and so it has to drop back down to its original energy level. And as it drops back down from the higher to a lower energy level, energy is emitted because there's a difference between the higher energy level and the lower energy level. So energy is emitted in the form of visible light energy, and that visible light energy has a wavelength of the observed light. So for lithium, when it drops back down to the lower energy level, the wavelength of it will correspond with a scarlet red colour. So now we're going to move on to some questions. The first question, which of the following is the correct equation for the decomposition of the corresponding nitrate? So we have our two rules of decomposition of nitrates. The first rule is that group 1 nitrates will decompose to form the nitrate 3 salt and also oxygen, whereas group 2 nitrates will decompose to form that group 2 oxide, oxygen gas and nitrogen gas. And so by working out which groups these nitrates, well, the metal nitrates are in, will give us the answer. And so lithium is in group, actually I'm going to write it to the side. So lithium is in group 1, sodium is in group 1, magnesium and barium both in group 2. So immediately we can rule out D, because we know that group 2 nitrates have to decompose to form the group 2 oxide, nitrogen gas and oxygen gas. So we know that no nitrogen gas is formed, so this must be wrong. And then looking at B, sodium is part of group 1, so it should only form the nitrate 3 salt and oxygen, but it forms nitrogen dioxide, so that must be wrong. And now we have to look at A and C to see which one matches. Because magnesium is in period 2, this equation that we have for C should be producing the nitrogen gas, oxygen gas and magnesium oxide, but it's not, so that must be wrong as well, which leaves us with the right answer, which is A. However, you might think that this is wrong because lithium is in group 1, but we need to remember that lithium is an exception to the rule, and lithium decomposes like all the group 2 ones do. Before I move on to question 2, feel free to click off the video and try it for yourself first. So the chlorides of magnesium and calcium can be distinguished from each other by carrying out a flame test. For A, describe what you would see in each test. So we know that magnesium burns with a flame with no colour. So flame will have no colour for the magnesium, whereas for the calcium it burns with a brick red colour. So flame will be brick red for this calcium. And then for B, explain how flame colours arise in a flame test. So basically what happens is that when they're heated, the electrons, which are free to move, rise up in energy level, and then they move back down eventually because they're unstable at a higher energy level. And so the difference in energy emitted as light. And so what we have first is that electrons are promoted to higher energy levels, but are unstable there. So then the electrons fall back down to the original energy level that they were in. And so the difference in energy is emitted as light energy.